Welcome back everybody. This is another video on the Velocity Boys, and today we're going to be reviewing some thermal physics for MYP. And so straight away we're going to start off with the very basics. What is temperature? How hot or cold something is. That's correct on the macroscopic properties of temperature. But really when we look at it on a particular level, what we find is that temperature is the average kinetic energy of particles in a system. So if I have a cup of coffee over here, as you can see, it's quite hot, which you can see the little eddies of steam going out of it. And when you touch it, it feels hot because the particles in the coffee, right here, are swimming around and basically moving at a very high speed, with a very high velocity, which causes their kinetic energy, which you should remember is from mechanics. Kinetic energy is equal to half times an object's mass times the square of its velocity. And so kinetic energy talks about the energy that particles have as a result of their motion. And so it's the motion of particles that leads to temperature. And so we measure temperature in the units Celsius and Kelvin. You should all be familiar with Celsius. That's what we use in our everyday lives. Maybe you use Fahrenheit with an F and a degrees, but we don't talk about that in physics because those are stupid forms of measurement. And what's the difference between the two? So Kelvin is an absolute measure of temperature or heat in an object, of the kinetic energy of a particle. So what that means is that if an object has 0 Kelvin temperature, right, like if I had this cup of coffee and its temperature was 0 Kelvin, it would mean that the particles had no kinetic energy. They weren't moving at all. Meanwhile, 0 degrees Celsius does not mean 0 kinetic energy. So, as it turns out, Celsius is related to the melting point and boiling point of water because having it scaled up from Kelvin makes it much more friendly for everyday use. Now, the thing to remember is that 1 Kelvin, the absolute value of 1 Kelvin, is equal to 1 degree Celsius. And what I mean by that is that they scale the same. So, if you have a temperature difference of, let's say, going from 50 to 70 Kelvin, right? If you have a change in temperature from 50 to 70, then you have a temperature change which is equal to 20 Kelvin, which you can write as, delta T, which will also be equivalent, hang on, let me use a darker color, which will also be equivalent to 20 degrees Celsius because they scale the same way. The only difference is obviously, like I said, with the scaling. So what we have is that 0 degrees Celsius, let me go back to my marker, is equal to 273 Kelvin. So if you want to convert between Kelvin and Celsius, so if you have X Kelvin, and you want to convert it to degrees Celsius, you simply add 273. So you do X plus 273 equals your temperature in degrees, and that's how you convert between the two. But it's important to remember and not confuse between the two. If a question asks you for the net amount of heat, you always, the absolute value, the actual value of temperature, then you want to use Kelvin. If it's asking for temperature change, then you can use either. And that brings us to the next point. What's the difference between heat and temperature? And so over here what we have is two masses of water. As you can see, we have the first one here, which is a relatively small body of water. It has a low mass, has a temperature of 50 degrees Celsius. On the right, we have a really big mass of water, like a big pool or something, but it has a lower temperature of 45 degrees Celsius and a greater mass. So the question is, which one has more heat energy? Now obviously you can see the answer here, uh, that the one on the left has less overall heat energy while the other on the right has more. But why is that? So the reason for that is because when we talk about heat energy in total of an object, we're talking about two things. Two things. So the first is, of course, the temperature. Temperature, right? If something is hotter, it has more heat. But the second thing also we want to remember is mass. Because you see, if I have something, let's say a cup of hot coffee, and one drop of it falls on my hand, it might sting a bit, but I'll be fine. But if the entire cup of coffee falls on my hand, then it's obviously going to have, be very damaging, and I'm probably going to get severely burned. And so the reason for that is because the amount of mass, again, if we go back to the kinetic energy equation, half mv squared, determines, or at least is related to, the amount of kinetic energy of particles, right? So if you have more mass, you just have more particles, you're going to have more kinetic energy. And so this big pool, even though it has a lower temperature, because it has so much more mass, it's maybe, I don't know, just, approximately 10 times bigger than this small one. Simply because of that, it's going to have much more heat energy. And that basically concludes our first part of thermophysics. Okay, so now we're going to move on to our second part. And the second part is going to be about heating, and specifically about this one thing called specific heat capacity. Specific heat capacity. So suppose I have a container over here. Alright, I have a pot. And I have a pot over here. Okay? In this pot I have water. And in this pot I have some oil. We have the same mass of water. So we have 100 grams of water. We have 100 grams of oil. Okay? And it's in a pot. And now what I do is I put this on a stove, okay, on a stove top, and I turn on the flame, and I ensure that both pots are getting the exact same amount of energy from the bottom. We're using the exact same pot, the exact same burners. We're assuming that all the conditions here are the same, except for the material itself, what we're heating. Now, eventually what happens is we start with both pots at 20 degrees Celsius each, right? And after 5 minutes, what we find is that the water has increased in temperature and is now at 85 degrees Celsius. But the oil has actually shot up to about 105 degrees Celsius, right? And so after an equivalent time of heating, after 5 minutes, for both of them, the pot of oil has actually heated more, even though it was getting the same amount of heat, same amount of mass, everything, right? But its temperature is higher, but the temperature of the water is lower. Why is that? Why is it that this material heats its temperature increases at a slower rate than oil? What if we had, say, a metal? What if we had, I don't know, steel? What if we had wood? What if we had, any sort of anything which we're heating, which we want to heat? Moreover, how can we measure how much it's going to heat up if we know a couple of things? One of them is, of course, its mass. Another thing is how much heat we're giving into the material of a given mass. And finally, one last thing, which we're going to call specific heat capacity. And so, what is specific heat capacity? Simply put, specific heat capacity is the amount of energy required in joules to heat up 1 kilogram of a given material by 1 degree Celsius. Alright? That is a definition, and that is something you need to know. Alright? And so, when we have that, and of course, one thing you have to remember is that the units, of course, are subject to change. You know, I could always say kilojoules here, and I could say gram here, or something like that. But the key thing to realize, here you have energy, here you have mass, and here you have temperature. Alright? So C is equal to joules per kilogram degree Celsius. Alright? And we're going to put that in a bracket here. And when we realize what this means, we can create an equation which looks something like this. It says Q equals mc delta T, where Q is the energy change, rather. We're going to call this the energy change of a substance, the change in heat energy after an object is heated. Here we have the mass. Here we have C, the specific heat capacity. So I'm just going to write that SHC. And finally we have the change in temperature. And what this helps us do is determine any one of these variables given the others, right? So if I have, let's say, let's go back to the pot of water again, right? If I have this one, and then if I have this oil here, oil, we have water, we have a certain amount of energy called, you know, some amount of kilojoules coming into some amount of grams, or, you know, the other way around, doesn't really matter. Here we have grams and we have some amount of energy. What we're saying is that because the specific heat capacity of water is greater and the specific heat capacity of oil is lower, as you can see here, for the same amount of energy, if this is constant, if C goes down, then the temperature change, assuming mass is also constant, must go up again, so that the equation can hold true, right? So if we have a higher specific heat capacity, what we're saying is that you need to put more energy into water to heat it up, and so the delta T is lower. Whilst for oil, because you don't need as much energy to increase its temperature, the speed at which the particles are moving, delta T is higher. And that's why, if we go back to our previous example, which is over here, we find that, it's not here anymore. Alright, but we find that the oil heats up faster. It goes, instead of 85, it goes to 105, because of that simple reason. Okay, and when we have, once we understand this equation, we can actually do quite a few things with it. And so now let's go over some problems related to this. Okay, so this is our first question about specific heat capacity, and as always, try and solve the question yourself first, and then you know, pause the video, solve the question, and then resume it, and then we can basically review the answer together, right? Anyway, so let's solve the question now. So a piece of metal of mass 0.2 kilograms is heated to a temperature of 200 degrees Celsius. It is then put into 0.2 kilograms of water at 20 degrees Celsius in a container of negligible heat capacity. The maximum temperature of the water after stirring is 40 degrees Celsius. calculate the specific heat capacity of the metal. Okay, so let's look at what we know. All right, let's first look at the metal. What we do know is we know the mass. We know that it's 0.2 kg. Okay. We want to find out the specific heat capacity, so we don't know that. We want to find out, we already know the temperature change. It is, well, it's at 200 degrees Celsius, and it cools down to 40. So the temperature change is 160. Okay? Then we know that the water here has a mass of 0.2 kilograms as well. We also know that the sea of water, which, by the way, you should probably memorize this because you're going to encounter it quite often. It's 4.2 kilojoules per kilogram Kelvin. So we can also write that as 4.2 kilojoules, and then use scientific notation. So do that. That's usually easier to write. Anyway, so we know that, and we also know delta T is equal to 40 minus 20, right? Because it starts at 20 degrees Celsius here and gets heated up to 40, right? Okay, so we know that. Now, what we want to do is use the information which we have of the water to find out the specific heat capacity of the metal. So the thing that you have to realize about this question, okay, is that if we have this glass of water and we put the metal into it, right, the energy gained by the water, so the delta Q of the water, equals the delta Q, the change in heat energy of the metal block, right? Of the metal block, because the only where is this water going to get its energy if not from the block, right? That's where it's getting that's the block is the reason why its temperature is going from 20 to 40. So if we can find the amount of energy which the water gained, we can set that to equal the energy that the mass of metal lost, right? And so what we can do is we can basically say this, all right? We can say that MC, so over here we can say so we can take the metal equation and we can say 0.2, and I'm going to write this actually in a text, so you can say 0.2 times C times 160, because that's the delta temperature, equals 0.2, because we have 0.2 kilograms of water, times 4.2 times 20, because 40 minus 20, right? The water changed in temperature by 20. And so from there, we pretty much got it. All we have to do is simplify from there. So I have 0.2 here, I have 0.2 here, so I'm just going to remove both of them because they're, again, both the same mass. So now we have that. And so we have C equals 4.2 times 20 over 160, which we can further simplify into 4.2 times 1 divided by 8. And you can obviously stick that into a calculator, but that will give us a value which is roughly equal to 4 divided by 8, right? So that will give us 0.525 kilojoules per kilogram Kelvin. And that is our answer. Or if you want to write it in terms of joules, that's simply 525 kilojoules per kilogram Kelvin. And so that's how we do a problem like that. It's a little bit more challenging because what you have to because it doesn't just tell you the numbers and ask you to compute it. Instead, it asks you to realize that make an observation and actually realize and form a relationship that the energy gained by this water should be the same as the energy lost by this piece of metal, right? And that's really the hardest part of the problem. Once you reach this equation, right? once you reach this equation, and you say that the energy gained by this equals the energy lost by this, you're basically done with 90% of the question. After that, it's just plugging in the numbers into a calculator and then getting the answer. So that's how we do a question like that.